All right, Michael's already starting it, so that's cool. So the next one is OVN expression parsing, fighting inequality by Ilya Maximets. Take it away.
Hi, I'm Ilya Maximets, one of the OVS maintainers, and today I'm going to talk about expression parsing for OVN logical flows, in particular the issue with inequality matches and the flow explosion. Let's start. If you open Kubernetes documentation for network policies, you may find an example similar to this one. What we can see here is that we are trying to allow egress to a certain IP block with /16 subnet, except for a certain /24 subnet. If you try to install this network policy in OVN Kubernetes cluster, OVN Kubernetes will create an OVN ACL for this network policy. If we only had a simple CIDR /16, we would have a pretty simple OVN ACL match as well. However, when we add an accept match, we also need to add an inequality check for this particular CIDR that we are trying to exclude from the subnet. If we add more than one, then we'll need to check for more than one as well. It seems pretty straightforward and seems to scale quite well. There should be no significant issues at this point. However, OVN ACL matches has to be processed by OVN itself and translated into OpenFlow rules. For example, the following ACL match will just be translated pretty much directly into an OpenFlow rule of the same form. However, once we add an inequality check, we suddenly get 8 OpenFlow rules instead of 1 or 2. Adding more subnets into accept block, we now getting 42 OpenFlow rules. With 3, it's 150 already. Doesn't look right, doesn't scale well. And if we continue an experiment, try different numbers of excluded CIDRs, we'll get pretty high numbers. And these are for /24 accept CIDRs. If we'll try to accept single IP address, for example, /2032, numbers will go even higher, a lot higher. And time to compute all of that for OVN-controller will also skyrocket to minutes. But looking back to the original network policy, we only had /16 CIDR here that contains only 65,000 IP addresses. So if we write a separate OpenFlow rule for each and every one of these IP addresses, we will get only 65,000 flows. But we are getting 1.7 million. How does that work? And something definitely not right here. But in order to figure that out, we first need to understand how exactly OVN translates those expressions into OpenFlow rules. First, we need to note that OVN logical flow expressions have a very rich syntax. We can have set matches, ranges, a lot of parentheses and nesting and checking on different fields, while OpenFlow only allows exact or masked matches on particular fields. And that's a big restriction. So how can we translate one into another? Well, first we need to somehow get rid of all the comparison operations that are not an exact or masked match. Let's take a look at the sets. Sets are fairly straightforward. Each set can be split up into several separate checks. For example, if we want one or another IP address, we can just write 2 matches for first of them or the second of them. And this directly translates into OpenFlow. without many issues. What about range matches? These are a bit different. Here we'll have to look at the binary representations of those numbers. In this example, we want values between 433 and 1024. Here there are binary representations of these numbers. If we'll start going bitwise from the least significant bit to the most significant in the smaller number and flip zeros to ones and mask the rest of the bits, we'll get masks for subsequent numbers in the set, in the series. For example, when we flip the second bit from 0 to 1 and mask the last bit, we will be able to match on a range from 434 to 435. If we do the same on the third bit, we'll include the range from 436 to 439, and so on, until we get the final range from 512 to 1023. We're not going any further because the next value will be higher than our upper bound. And as you can see, we now have a set of masks, of values and masks that will cover the entire range that we need. And those can be represented as bitwise masks, as bitwise matches. So our range match translates into 5 separate bitwise matches that translates directly into OpenFlow. What about inequality? Let's look at the simple example where we only want to match on first 8 bits of the destination port, and we want it to not be equal to 177. We still need to look at the binary representation of the number that we are looking at. The key of the inequality match is that if at least one bit of our value is not the same as what we need, then the whole match is not equal. So if the last bit here is not equal, if bit 0 is not equal to 1, it means our value is not equal to 177. The same goes for second bit. If the second bit is not equal to 0, then the whole value is not equal to 177. And so on and so on. We can write it down for every single bit that we are trying to match on. But we still have an inequality in the check. But now it's easy to get rid of it because inequality on a single bit is equivalent to equality on the opposite value. So if this bit 0 is not equal to 1, means that this bit is equal to 0. So just flip all the bits. And now we have 8 rules that no longer have inequality in them, which are simple and can be represented as a simple bitwise check. So our inequality match on 8 bits translates into 8 equality matches on the whole field and translates into OpenFlow rules. The main problem here, however, is that number of OpenFlow rules directly depends on how many bits we are trying to match on. So that was the first step. Second, we need to normalize the expression. Let's say we have the following fairly complex expression. We are trying to match on IPv4 packets from localhost or another local address, and it should be ICMP or a TCP packet with destination of HTTP or HTTPS port. Looks reasonable. For simplicity, let's replace all the individual simple matches with just letters. So our expression looks like this. Rewriting it in slightly more mathematical way and starting to normalize it. First, we can open up innermost parentheses, then the first parentheses, and the last one. Ultimately, we should get something like that, which is normally called disjunctive normal form. And disjunctive normal form exists for every Boolean formula, so we are covered. Let's now remember what was the actual values of our letters, and every single term in this disjunction will end up as a separate OpenFlow rule. For example, our ABD translates into IP network source equals localhost, and it is an ICMP, since D means ICMP. So in the end, our total OVN logical flow match translates into 6 OpenFlow rules. So let's try to apply all that knowledge onto our original OVN ACL match with just 2 CIDRs to be excluded from the larger /16 subnet. First term here is fairly simple. We don't need to do anything. It pretty much directly translates into OpenFlow if needed. The second part is fairly complex. Let's remember what our first step is to get rid of all the complex matches. We see here the set. First, we need to get rid of that. Or replace the set with 2 separate inequality checks. And now we need to get rid of those inequality checks. This is about to get messy because each of them is matching on 24 bits of the IP address that we need to substitute, and the second one as well. That seems like a lot. However, we have our first term here, which is restricting all the IP addresses to the /16 subnet. And if we look at what's inside of parentheses, we see that all these bits from 16 to 31 will be inconsistent with our first term of the match. Let's just get rid of those, as they will not contribute anything to the end result. I'm not going to actually open those parentheses now, because it will take a lot of space and time. We just count how many terms in the resulted DNF we will have. Here we have the first term times 8 terms in the first parentheses and 8 terms in the last one. 64 terms after opening parentheses here. Almost half of them will be exactly the same though, because most of these bits are the same in both, only the bit 9 is different. So we'll have checks like bit 8 equals 0 and bit 811 equals 1 twice in the opposite order. Order doesn't matter for our Boolean formula, so we can just remove all these duplicates. However, bit 9 is different, as I said, so we'll end up with 44 and not 32 rules. Now, what happens if we use /32 instead of /24? In this case, we'll also need to match on low 8 bits, and computation will get 16 times 16, so 256 terms instead. In practice, we'll get 150 or something OpenFlow rules in the end. And what if we also remove the original restriction on the /16 subnet? Well, in this case, we will also no longer be able to assume the value of the top 16 bits, and we'll end up into 32 squared, which is 1024 terms in our DNF. And these numbers are for just 2 excluded CIDRs. And this number hits 1 billion with just 6 of them. This obviously doesn't scale. And visible side effects of installing so many OpenFlow rules is high CPU usage on OVN-controller, obviously, to compute all of them, high memory usage to store all of them, and also high CPU usage on OVS vSwitch itself. Packet classification becomes expensive in OVS because all of these rules are likely going to be installed into the same table and they are all matching on the same fields. And this will cause potentially OVS handler and revalidator threads to consume a lot of CPU cores. What can we do? So let's look at what within a simplified version of what we had. Just 3 bits, 8, 9, and 10. Bits 8 and 10 are the same in both parentheses, and bit 9 is different. So let's expand that, and we'll have 9 terms. Some of them are exactly the same, as I said, so we can remove the term 7. The term 5 is also inconsistent because it matches on the same bit but different values. We can remove that. At this point, OVN 2303 and below doesn't perform any further optimizations, and you will pretty much get 7 OpenFlow rules out of this. But can we do anything else here? Fortunately, the answer is yes, we can. Let's look at the first and the 7 terms in our expression. They are matching on the same bit twice, so we can just rewrite this in more compact form. But now it should be easy to see that a lot of these terms are actually matching on the same bit. So we have the term 1 that matches on bit 8 to be 0, and terms 3, 4, and 5 also matching on the same bit to be 0. And remember, this is a disjunction, so we only need one of them for the whole disjunction to be true. So if the bit 8 is 0, then all of them will be true. And if 3, 4, 5 are true, then bit 8 is 0. That means that 3, 4, 5 are actually redundant here and can be removed. And same goes for bit 10. We have 3 and 4 matching on bit 10 to be 1, and they can also be removed. So now we have just 2 terms out of 9 remaining, and that's a big improvement. So let's see what happens if not only one bit is different. So here we have bit 8 is the same, bits 9 and 10 are different. We can no longer remove the term 7 because it's no longer exactly the same. However, we now have 2 inconsistent rules that can be just removed. And we still have one term that matches on bit 8 twice. It can be shortened. And we have 4 other rules that match on the same bit that can also be removed. And we end up with 3 rules, 3 terms out of 9. That's also good. However, we should notice that more different are the initial values, more rules will be required. And that's a significant restriction on what we're trying to achieve, but at the same time, we are assuming that it's most likely will have fairly similar, at least part of the field that we're trying to match on, so it should not be a big problem. So let's summarize what exactly we just did. So the optimization steps are to sort the terms based on the number of bits in the mask. If you remember, we moved terms that match on a single bit to the beginning. Then starting from the smallest, we eliminate all the larger terms that are supersets of the current one. Then pick the next smallest term and repeat the operation until we have something to remove. This is something about n² complexity in the worst case. However, we are assuming that a lot of bits will actually be equal in the process of opening those parentheses. So actual complexity in the real world scenarios should be much, much lower. And we're also using array-based lists with path compression to make computations faster. Luckily, people are not using sets of completely random IP addresses. So let's see what we achieved with this new version. This is our old table for accept CIDRs /32 individual IP addresses. With just one, we had 16 OpenFlow rules before, and now we still have 16. That's fine. With two, we only got 15 rules with a new optimization in place, which is a 10 times improvement. Before it's just 14 because we, for some reason, we managed to cover some of the gaps between masks and actually reduced number of flows. And same goes for up to 32, which I tested. So we still have fairly reasonable, just 31 OpenFlow rules for 32 accept CIDRs, which is great. But yeah, going back to restriction that's more different our initial values, more OpenFlow rules we'll need. If we'll just randomly generate a lot of IP addresses without much restrictions, we will still get a lot of OpenFlow rules, and it will take a lot of time to compute. However, even in this case, we are looking at a much less amount of OpenFlow rules that we had before. So conclusions, don't write ACLs like that. Yeah, seriously, don't write ACLs like that. Use priorities instead of negative matches. Use something like deny all plus allow specific IPs. This is supported on any version of OVN, so just use those if possible, and you'll avoid the problem altogether. Use new tiered ACLs introduced in OVN 2306. Use Kubernetes admin network policies, which is a new way for defining network policies for admins in Kubernetes clusters that will actually use tiered ACLs and priorities under the hood. And try to split large ACLs into smaller ones if possible as well. That might help reducing the explosion, this computational explosion. And if none of the above is possible, make sure you're on OVN 2306 Plus to get the best possible performance. That's all, and thank you. And special credit to Nadia for highlighting unoptimally generated OpenFlow rules that led to this improvement in the end. Thanks.
All right, thank you, Ilya. And also thanks for explaining everything in great detail. I think it helped a lot for me to understand some of the issues you're facing with. So the thing from my side as well. I see we have one question, or we have multiple questions coming up, but the first question I have is from Mike Patrick, and he says that the OVS classifier already supports conjunctive matches. Would adding support for negative conjunction matches help simplify the negative matching?
So it's an interesting idea, and actually, I skipped one thing that OVN does already. So OVN already is using conjunctive matches in some cases where it is possible to split variables into separate disjunctions that do not overlap by the fields they match on. In this case, OVN will actually produce OpenFlow rules with conjunctive matches. However, the problem with that is it's not always possible. As I said in the presentation, we are kind of covered from the math standpoint that disjunctive normal form exists for any Boolean formula that we have, so we can always construct this. However, we are not actively trying to build this conjunctive form. and optimization is only applies if we happen to have it. And unfortunately, in many cases, it is possible to just slightly adjust the expression for optimization to no longer be possible. But yeah, that's an interesting thought. I didn't think through if the negative conjunctive match is something that we can do, but yeah, we can explore. Though negative conjunction sounds a lot like disjunction to me.
All right, thanks for answering that question. We have another question from Dumitru. Can we extract the expression parsing optimization into a library tool that can be used by the CMS to build optimal ACLs from the beginning?
That's an interesting thought. I think one problem with that would be that it's written in C, and most CMSs that I know of do not use C as their primary language, so it might be a separate binary. However, I'm also not sure how exactly that would work. We are translating into OpenFlows directly, so it may be possible. Yeah, I'm not sure if it gives a lot of value for users, and also it will degrade abilities to debug, because you may have something not very intuitive at the end of the expression modification, when all the parentheses are open, or when we create all the bitwise masks and stuff. It becomes less obvious what we're actually doing. It's already a slight problem on the OVS level, because we have all these strange OpenFlow rules, and it's hard to tell from where exactly they came from. And if we introduce that on the CMS level, that might elevate the problem to a different level as well. So yeah, it's an interesting thing to think about. Yeah, I agree. It's something worth investigating, but we also need to be aware of potential issues.
All right. Thanks for answering the question.